Iron is one of the most abundant metals in the universe. It's so abundant that materials that survived the creation of our own solar system, like the meteors of the famous Kuiper Belt, are made primarily of this metal. Every now and again, one of these meteors gets pulled into the interior of the solar system by the gravity of the Sun, very rarely colliding with Earth, and giving us a peek into the materials from which our own planet formed. The Earth formed in a process known as accretion. Particles of the same stuff as those meteors collided with one another and heated up, creating a hot ball of rock with a gravitational pull that grew with each impact, attracting more and more material. Now, some of that material was iron. And although much of it settled into the core of the planet while it was still molten, there were still plenty of iron-rich meteorites impacting the Earth as it cooled, leaving huge quantities of metallic iron at or near the surface as continents and oceans formed about 4 billion years ago. So where's all the iron now? When we take a look around natural environments, we don't see much metallic iron hanging around. Well, the inconvenient truth is that early oceans were very acidic and lacked oxygen. As Earth settled into the calmer part of its lengthy lifespan about 4 billion years ago, much of the pure iron, what we would call native iron, near the surface was dissolved away by oceans and rainwater, becoming concentrated in the oceans of the Earth. There's powerful evidence for this in the form of banded iron formations, thin layers of iron-containing minerals deposited as photosynthetic bacteria battled to gain a foothold on Earth about 2 billion years ago. As these bacteria began to grow and spread, they produced oxygen, which reacted with the iron in the oceans, creating insoluble iron oxide minerals. As the cyanobacteria population and activity ebbed, more iron dissolved into the anoxic oceans, only to be precipitated from the solution by the next wave of biological activity. Now, this resulted in a beautiful geological feature known as banded iron formations, alternating thin layers of iron oxides and silicate minerals which date to about 2 billion years ago. These remarkable geologic creations testify to the struggles of early life as it battled to terraform the Earth into an oxygen-rich world, ready for the evolution of a higher order of life a billion years later. Today, humans dig these iron-rich minerals from the ground to take them to foundries designed to reverse that process that got them there in the first place. And this, of course, is a quest to recover the iron for use in building cars, buildings, and so much more. This lecture is dedicated to the reaction that put all of that iron in the ocean in the first place, and other reactions like it. Today we're going to discuss reduction and oxidation, or redox reactions. Small, fast-moving, and negatively charged, electrons are usually held tightly by the nucleus to which they belong, giving a given element many of its properties. But we already know that electrons aren't confined to a single atom or even ion. Electrons are often exchanged between and among elements in chemical processes. The most notable example of this so far has been our example of ionic bonding, in which electrons are exchanged between two neutral atoms to form ions. But that only scratches the surface of the complex chemistry that can happen when electrons are on the move. Think about the metals that are used to make coinage for a moment. Gold, silver, copper, platinum. Aside from their relative rarity and beautiful luster, there's another reason that historically these metals in particular are used to make most of the coins used by society as currency. For a coin to have value, it has to last. There were other metals available to early cultures, metals like iron, but those metals are prone to react with oxygen in the air, or even the acids and moisture carried by human hands. Over time, they would become dull, their impressions worn and sometimes lost. And this process is the result of iron atoms, for example, losing electrons, ultimately to oxygen, to form a new compound in which the iron is now an ion. We've seen an even more accelerated example of this process when we discuss periodic trends. The alkali metals that we investigated lost electrons to become ions during that demonstration. Now, in this case, they were reacting with water itself, a very stable material. Even so, the electrons were lost. So certain metals are more quick to give up their electrons to form ions. And when we organize them in a column from the most reactive to the least reactive, we get what's called the activity series. The activity series gives us a useful guide to compare how easily a metal will become a cation. We can use this table to determine whether or not certain metal substitution reactions will take place. A reaction in which one metal ion meets another metal in its neutral state, and the two switch roles by electron transfer. We simply treat the reaction like a tug of war for available electrons. Who wants them more? For example, a sample of solid zinc in the presence of a copper sulfate solution with copper ions will dissolve and form zinc ions as the copper precipitates from the solution. Why? Because copper is lower on the activity series. It wins the contest for electrons with the zinc and it becomes neutral, losing its stabilizing ion-dipole interactions within the water. This makes it come out of solution. But if that zinc is instead dropped into a solution of magnesium nitrate, nothing happens. Magnesium metal is higher on the activity series, so it's more inclined to stay ionized and let zinc keep its electrons. The activity series also predicts that we should be able to clean tarnished silver using something as simple as aluminum foil. Right? Silver tarnish is actually silver sulfide, an ionic substance in which silver is carrying a positive charge. But by contacting tarnished silver with aluminum foil via a hot solution of baking soda, the two metals can be made to exchange electrons, forming aluminum ions and recovering the metallic silver that gives your silverware its attractive shine. The activity series also naturally clusters metals into groups based on their reactivity with other common materials. Those that do not react to produce hydrogen gas at all. Those that react with acids to form hydrogen. Those that react with acids and steam to form hydrogen, and those that will even react with liquid water itself to produce hydrogen gas. But there are far more redox processes to consider than our simple activity series here might indicate, so we'd better move on here. Chemists break these types of changes down into two fundamental types of electrochemical processes: reduction, in which electrons are added to a substance, and oxidation, in which electrons are removed from a substance. For example, here's an atom of iron. It has 26 electrons in its neutral form. But in one of its more common dissolved forms, it's missing 2 of those electrons to form iron 2+. So iron just lost 2 electrons to become a divalent cation, meaning a +2 charge. Chemists call this process of losing electrons oxidation. In other words, I would say that iron was oxidized to iron 2+. You might be asking yourself right now, oxidation, where's the oxygen? Well, oxygen doesn't have to be participating in a process for electrochemical oxidation to take place. The name stems from the strong power of oxygen to carry out this process on other materials, but there are many others that can get the same job done. In this depiction, electrons from iron just flew out into space. That doesn't seem very scientific, does it? I think there's a logical question here. Where did they go? Well, electrons don't just leap out of atoms for no good reason, and they certainly don't just disappear. They have to have a destination. In the case of our weathering iron metal, the destination is the protons of the early acidic oceans and rainwater. But as scientists, we want to understand the driving force. So let's take a look at that reaction in detail. Now we're ready to put a number to this so-called electron motive force that's going to drive the reaction forward. And we're going to do it with our very familiar reaction, the dissolution of iron in aqueous acid. Now, remember, we've already gone through the process of being absolutely certain that this reaction is charge balanced and mass balanced. We already know how many electrons are being used in the transfer here, right? Remember, we did this previously. So here again is my oxidation half reaction, in which iron is oxidized to iron 2+, and then it's going to act as a reducing agent. Here's my reduction half reaction, in which protons are being reduced to hydrogen gas, and therefore will be an oxidizing agent in the overall reaction. And I've included a little bit more information here, and that is, these are called half potentials, or half cell potentials, if you will. They're always written in the direction of reduction, which is a little bit unusual, right? Because we have an oxidation reaction here, in the case of iron, and yet I'm telling you the potential for that reaction as a reduction. Now, the reason for this is simple, because it keeps the table smaller. There's no need to report both the reduction potential for the reverse reaction and the oxidation potential for the forward reaction when we can simply remedy that by flipping a sign. It's really that simple. So even though this here says negative 0.440 volts, it's up to me to realize that we're dealing with an oxidation, and therefore this reaction is actually plus 0.440 volts of electromotive force. We also have a very fortunate situation in the case of our hydrogen ion to hydrogen gas reduction half reaction. And that is that this is the defining reaction. This is the one that we use and set arbitrarily at 0.00 volts. All other cell potentials are simply a comparison to this one in particular. So this will make our math fairly simple. And here's how we use the electromotive force to determine whether or not a reaction will take place. The potential for the entire reaction is simply the sum of the electromotive forces for both half reactions. In other words, E naught for the overall reaction is equal to the reduction potential for the reduction plus the oxidation potential for the oxidation half reaction. Well, that's great. That's a pretty simple mathematical relationship. All we have to do is add. But there is one gotcha here, and that is you've got to be careful about your signs. The reduction potential here listed is negative, meaning the oxidation potential from this equation down here is actually positive. Now, I can fix this in a number of ways. One way I can do this is simply say, well, okay, instead of adding the oxidation potential, let's subtract the reduction potential. Mathematically, that should give me the exact same answer. Right? The other way to do it is to come up here and look at the reduction potential and say, I already watched this lecture, right? I know that this is supposed to be positive if I'm having an oxidation half reaction. So let's do both of those. In this case, if I add the oxidation potential to the reduction potential, that means I'm adding positive 0.44 volts to 0, which is my reference standard for hydrogen. If instead I decide to use the lower equation, right, this time I'll be subtracting that reduction potential, which is already negative in my table, which tells me I'll be subtracting negative 0.440 volts. Now look at this. Mathematically, they're identical. Adding 0.44 is exactly the same thing as subtracting negative 0.440 volts. So whichever of these two tickles your fancy, both of them will work because they're mathematically equivalent. And both of them tell me that the potential for this reaction is plus 0.440 volts. That means that there is a positive electrochemical potential pushing the reaction forward. This means that in those early acidic oceans, there definitely is enough electrochemical potential there to get iron to dissolve. So in my overall reaction, 1 mole of iron becomes 1 mole of iron 2 plus ions, just as 2 moles of hydrogen become 1 mole of hydrogen gas. The reduction half reaction is that of protons to hydrogen gas, and the oxidation reaction is that of iron to iron 2 plus ions. Now our metallic iron is dissolved into our early Earth ocean, awaiting its destiny of becoming part of a banded iron formation when dissolved oxygen is available. In our example here, it's very clear that electrons have been fully transferred from the reducing agent iron to the oxidizing agent protons. But it isn't always that obvious. Redox reactions can take place between and among covalent substances as well. A simple example of this is the combustion of hydrogen to form water. In this reaction, diatomic hydrogen and diatomic oxygen, each with oxidation states of 0, react to form water. Now, we all know that water is not an ionic compound, but if we were going to treat this reaction as a redox process, we'd have to ask ourselves, what would the charges be on those atoms if they were ionic? In this case, the answer is +1 for hydrogen and -2 for oxygen. Because oxygen's higher electronegativity gives it greater claim to the electrons participating in bonding, even if not giving it total claim to them. Now, using this simple method of assigning oxidation numbers, we can think of many different types of reactions in terms of reduction and oxidation. Our understanding of reduction and oxidation half reactions gives us more than just a way of describing where electrons are going. Once we have defined these half reactions, we can use them to predict the chemical potential energy behind any given redox process. We unwittingly did this in a qualitative level back when we explored the activity series of metals. Recall that when we did that, we saw how a metal like silver, being lower on the activity series, has a greater affinity for its uncharged state than does aluminum. We decided at that time that if silver ions ever met aluminum metal, they would want to switch places with silver becoming neutral metal atoms, and aluminum, of course, taking on the positive charge. This is absolutely true, as we can demonstrate using a tarnished piece of silver and a layer of aluminum foil. All we had to do was create an opportunity for the electrons to make their move by bringing the two samples into contact, and a reaction occurred spontaneously. If we think of this reaction as a flow of electrons from one element to the other, the system begins to look an awful lot like one of these. That's right, we can think of redox reactions almost like discharging a battery. The difference, of course, is one of scale. A single atom or ion exchanging electrons with another in direct contact. And that might not seem too exciting, but it is exactly the same process that's going on when you turn on your laptop or push the start button on your vehicle, with a few engineering tricks, of course, to harness that voltage. So, just like a battery, a simple redox reaction taking place inside of a flask between individual atoms and ions will have an associated voltage. Voltage is sometimes called electromotive force, or EMF. I actually prefer this term to voltage because it better describes what the term really means. It's a measure of the difference between the two agents' desire to possess the electrons being transferred. And if a reaction's EMF is positive, then the reaction will proceed spontaneously under that force. This EMF is much easier to observe when the reduction and oxidation processes are separated from one another. If the reducing agent and oxidizing agent are separated by a conductive substance, like a wire, for example, the electrons will have to flow through that wire from the reducing agent to reach the oxidizing agent. We call the side from which electrons flow the anode, and the side to which they flow the cathode. They don't necessarily have to be charged, but the names help us to remember which side is losing electrons and which side is gaining. If one side of the system wants electrons much more than the other, then a strong current would be observed because the EMF is greater. When both sides have similar desire for the electrons, little or no current would be observed because the EMF would be much smaller. So the EMF for a given redox reaction is all about relative desire for electrons. But that is enough anthropomorphizing. Atoms and ions don't really desire anything. They simply attract electrons with differing affinities. And as scientists, we want to quantify this. But how do we do it? The key is to realize that there are always two opposing forces acting on electrons in redox processes, one pulling them one way and one pulling them the other. We call those opposing forces half-cell potentials. And it's the sum of these potentials that tells us just how powerful the EMF will be for a given redox reaction under standard conditions. Let's analyze that driving force behind the reaction that we currently are discussing, and that is the dissolution of iron into acidic aqueous solution as iron 2 ions. Well, I've written my reaction here, but you should immediately notice there's a problem with it. I'm not balanced. I've got a situation where I have one iron and one hydrogen ion on my reactant side, but I have an H2 molecule over here as one of my products. So I'm going to have to make sure I'm balanced before I do any further analysis. We have a fairly simple atom inventory this time, iron and hydrogen. And if we look at both sides of the equation, we find that we have one atom of each as our reactant, one atom of iron, and two atoms of hydrogen in our product. This is a fairly simple solution. We just add a coefficient of 2 to our hydrogen ions. We now have a balanced overall reaction. But redox reactions need to be split in half, if you will, to be properly analyzed. And I'm going to show you why. What I'm going to do here is take just the hydrogen part of my reaction. Now in this case, to convert hydrogen ions into hydrogen gas, I'm going to need, of course, electrons. I have to add electrons and use them as though they were a reagent in order to get charge balance in my half reaction. And because I've broken it down into the half reaction, I know that I need 2 electrons to reach that charge balance. But that leaves a question. And the question is, have I written the reaction in such a way that iron is also having 2 electrons participate in the reaction, or am I going to have a charge balance issue? Well, in this case, we got lucky. What's known as the oxidation half reaction would be iron to iron 2+. And again, to charge balance my oxidation half reaction, I simply add 2 electrons, but this time I look at them as though they were products in the reaction. So here's my oxidation half reaction in which iron is being oxidized and therefore would be called a reducing agent. Here's my reduction half reaction where protons are being reduced and therefore they are the oxidizing agent in this particular redox reaction. And of course, I've just determined that my electrons are balanced. So now I have the proper electrochemical reaction and all the information I need to analyze the driving force behind it. We've already considered at least one redox reaction that involves iron. The one that took place over geologic timescales as early iron metal dissolved into the oceans reacting with protons. But not all redox reactions have to be that slow, not by a long shot. And to prove that to you, I'm back in Osmond Lab here at Penn State to show you what's called a thermite reaction. A thermite reaction is a redox reaction involving iron, but this time it's iron 3 oxide. So I have iron 3 ions, and they're going to react with aluminum metal. Now I want you to think about that for a moment. Aluminum is far, far higher on the activity series than protons are, which means that the aluminum should be able to react with iron, reducing the iron, and creating a redox reaction. But again, it looks quite different than the one that we discussed previously. So let's do the reaction. To do the reaction, I have a setup here that involves some ceramic bowls because there will be quite a bit of heat. And there are holes in the bottom of these ceramic bowls through which one of our products is going to fall into the sand in the beaker below. And I'll show you that when we get to that point. In the meantime, I have a mix of iron 3 oxide and powdered aluminum. And I have a little bit of magnesium that I'm going to use essentially as a fuse or a wick to introduce that little bit of energy that it takes to activate this process. And of course, I'm going to have to light the magnesium using a torch. All right, I'll begin setting up for the reaction by placing my thermite mix, which again is iron 3 oxide and aluminum metal, into my ceramic crucible here. All right. Oof, I don't want to get too much of that stuff in there. There we go. Make sure it comes out cleanly. There we go. Okay. Okay, next I'm going to place my wick in here. This is how we're going to get that first little bit of energy needed to start the reaction off, the activation energy. And then I'll tap this a little bit to try to get the powder level. Okay. And now we're ready to start our thermite reaction. All right, here we go. Now, considerable amount of energy was released in a very short period of time, wasn't it? Now, one of the products of this reaction is, of course, iron, because we have reduced the iron from iron 3 down into iron metal, and that's proof of it right here in the sand. As you can see, we've created molten iron in the reaction. So here's an example of a redox reaction that doesn't take place slowly over geological time, but incredibly rapidly, releasing a tremendous amount of energy, enough to actually melt the iron product that forms, which is one reason why these reactions were once used as a welding technique. So there are two very important differences that we need to remember for the remainder of our discussion of electrochemistry. First, we have to remember that half-reaction potentials are intensive properties. This means that they don't depend on amounts and are therefore not affected by reaction coefficients the way that enthalpy, entropy, and free energy are. Second, that greater positive potentials indicate progressively more spontaneous reactions. This is the exact opposite of Gibbs free energy values, which become more and more negative as reactions become more favored. This is a curious change from the norm for us, but we're soon going to see that this change in treatment can be accounted for later. Now, when we attempt to unify cell potential and free energy equations next time, we'll see how that works. But for now, let's sum up our discussion for today. Today, we started by asking the question of why we seem to find iron in its metallic state so rarely in nature. We saw how geologists theorized that the early Earth actually did have copious amounts of iron, not only in its core, but also at its surface. And that led us to ask the question, what happened to all of it? We saw how even in the oxygen-depleted environment of the early Earth, acidic solutions in water were perfectly suited to dissolve the iron by stealing 2 electrons from it to form hydrogen gas from protons. Then we took a look at some remarkable geological formations called banded iron formations. And these multi-billion-year-old relics of the Hadean and Archean periods give us a window into the struggle of life to stake its claim to the planet as colonies of cyanobacteria coughed oxygen into the environment, off and on again as they battled for their own existence. That piqued our curiosity about exactly how and why electrons move from one atom or ion to the next. We then used the activity series to explain a few simple substitution reactions, including that between aluminum metal and silver sulfide, which the series correctly predicts can be used to remove the tarnish from silver. Then we discovered that the activity series was just the beginning of how chemists characterize these kinds of processes. We learned how a whole class of reactions called redox reactions is characterized by the exchange of electrons, and how these reactions can be broken down into 2 sub-reactions called reduction and oxidation. Now, keeping in mind that electrons always have to come from somewhere and have a destination, we characterized reduction as the gain of electrons and oxidation as the loss of those electrons. We also saw how the reagent that takes on the electrons is called an oxidizing agent, and that which releases them is a reducing agent. And we saw how these 2 half reactions must always take place together. We saw how the electron motive force, or EMF, is essentially a measure of how forceful the flow of electrons from one redox reagent to another is. And finally, we saw how we can calculate the overall electromotive force for a redox process using the half reaction reduction potentials. Those are tabulated and very well understood for many reactions. When we did this, we made a special note of 2 significant differences between EMF and other thermodynamic properties like enthalpy and free energy. Specifically, we learned that multiplying a half reaction has no effect on its reduction potential, and that a positive EMF correlates to spontaneity. But we're just getting started with our discussion of how the exchange of electrons can power some of the most useful chemical reactions and devices conceived by man. Next time, we're going to meet a trio of influential scientists, an American, a Brit, and a German, whose relentless drive to understand the details of how and why redox reactions take place ultimately blossomed into the incredible science of electrochemistry. Redox reactions can be tremendously important from industrial perspectives, and understanding them helps companies to save money and in some cases harvest some of their waste products to get useful materials back. Now, a very obvious example of this, or a very good example of this at least, is a process known as copper cementation. Now, copper cementation is used to recollect dissolved copper ions from industrial waste. And it's done using knowledge about the activity series, right? Remember, iron is more likely to be iron 2+ than copper is to be copper 2+. So just based upon the activity series alone, I know that this reaction should take place. But let's analyze it a little bit more deeply now that we have a better understanding of redox chemistry. We're going to answer 3 questions about the process of copper cementation, in which these solutions are simply flowed over or sprayed onto metallic iron in order to allow this reaction to happen and create solid copper that can be recollected. Our questions are the following. What's the balanced half reaction for each of the 2 halves of my redox process? What are the reducing and oxidizing agents in this process? And what's the EMF for the reaction under standard conditions? So let's get started on solving that. First, my half reactions. In the case of this particular redox reaction, notice that copper 2+ is becoming copper 0. In other words, its charge is going down, which means it is reduced. That's my mnemonic for remembering this. So my reduction half reaction is copper reacting with 2 electrons to form the solid metal. Therefore, my oxidation half reaction is going to involve the iron. And in this case, we have iron metal, which is not charged, becoming iron 2+ and releasing those 2 electrons, which are, of course, going to react with the copper. So my reduction half reaction involves the copper. My oxidation half reaction involves the iron. That answers question 1. Now, question 2 is about what are the reducing and oxidizing agents. So let's answer question 2 now. And it's actually fairly simple to do this. Remember, if iron's getting oxidized, it is causing copper to become reduced. If copper is becoming reduced, it can be thought of as causing iron to oxidize. In other words, we simply flip the positions here, if you will. So our reducing agent in this case is going to be iron, and our oxidizing agent in this case is going to be copper 2+. So that answers question 2. Finally, we want to calculate the electromotive force for this reaction. Now, to do that, we have to go to our table of reduction potentials. So here's our total redox reaction. Let's figure out the EMF from tabulated reduction potentials. When I go to the tables, I find that the reduction of copper 2+ to copper metal has an E0 of 0.3 volts. Now, if I look in the same table, I'll be getting a reduction potential for iron, meaning going from iron 2+ to iron. But that number from my table is negative 0.44 volts. But I've got to be very careful to remember that's a reduction potential, and I have to be sure that I account for the sign change when I reverse the reaction. So, when I calculate E0 for the overall reaction, I'm going to use the reduction potential for the reduction half reaction, but I have to use the oxidation potential for that oxidation half reaction. In other words, I've got to be sure I subtract it and not add. So in this case, I end up with a positive voltage of 0.78 volts as the EMF for the overall redox process involved in copper cementation.